polar vortex had made its way through, and I actually think we've got one more on the way before spring. A year ago at this time, I think you Boston got hit, and I put this next slide in for David French. One time I was talking to him, and he said it was cold and just a figure of speech. So, in any event, it takes some of you a little longer to catch. But okay, so on with the presentation. The previous presentation actually was an ideal lead-in to what I would hope to say. And I guess the conclusion of what I'm going to say is probably going to lead to more discussion rather than conclusions. The benefit of these types of conferences typically is the opportunity to meet one-on-one and in small groups and talk about things. And I'm hoping that that's what this presentation leads to. So the summary is, a wide variety of co-deposition protocols have been used, and we just heard about another one. Magnetic, electric fields, ultrasonic fields, other forms of stimulation seem to be important. Fukai is a name that a lot of you probably haven't heard of, and I'm going to talk about some work he's done. He's a material scientist and did not know he was doing what cold fusion work at the time he did his work, and then the implications to these results. The evolution of co-deposition starting in '89 when Pons and Fleischmann did their result. Mike McCoubrey has a statement that says, any scientist worth his salt always has a better idea. They never follow what the other person did, and that was certainly the case with Stan Spock. He thought immediately that the better idea was co-deposition. In fact, while everyone else was out finding palladium rods or wires to do the experiment, Stan found some palladium chloride and did a co-deposition experiment. The first experiments that were done at the Navy lab, and for a long time, continue to work with that. Many others have used co-deposition, and I haven't attempted to list all of them, but I do want to focus in later on some work, recent work by Letz and Hagelstein. Was actually published in JCMNS in 2012, and was presented parts of it at ICCF 17 in Korea. I didn't pick up on the significance of it until just recently, or what I think is significant. This was one of the first co-deposition experiments that we did in San Diego with Pam Boss and Stan Spock. Took some palladium chloride, an electrode, a couple of thermocouples, and after very few minutes, you can see that the solution warmed up and was warmer the cathode was warmer than the solution. So this was not something that should happen. If you have joule heating, clearly the solutions should warm up faster. And so this was evidence that heat was being produced at the cathode. We did not even attempt to do precision calorimetry in San Diego. We just didn't spend the time doing that, but did a lot of work for just measuring the cathode. Also, here when we turned the experiment off, we saw the temperature rise on the metal and the cathode, and then the solution followed. This was the heat after death that Fleischmann talked about, and we were able to see that. And this was published in the Journal of Electrochemical Analysis in 1991. One of the other experiments we did a few years later was an IR examination of the cathode as it was going, and you can see, now this is in real time, so you can see in a matter of a few seconds how much the cathode was heating up, and Dave Nagel did some later analysis based on the size and the time and all that, and concluded that these had to be nuclear events that were causing this kind of heat production. We showed these results to Lowell Wood from Lawrence Livermore Lab, and he said, hey, you guys are in the Navy, you should put a transducer in there because if these are little mini explosions, you should hear them. We again, being scientists, thought we had a better idea, and that was to take the piezoelectric, ferroelectric material and co-deposit right on to that. And when we did, we were able to see pressure spikes followed by a thermal increase. And you know, piezo or pyroelectric materials, both piezo and pyro sensitive. And so it would measure both the pressure and also the temperature. When we looked at the different surfaces, you know, here's the co-deposition without magnetic and electric field. When we applied an electric field, we saw some different morphology, and a magnetic field clearly showed a different morphology. One of the features of co-deposition was it gives us a possibility or opportunity to really check and see what's happening with a lot of things. And these results again were published in 2005 and 2007, although the work was done in actually some of it fairly early in the 90s. When I talked to Stan about what are the electrochemical processes involved, and the typical protocol that we have used in San Diego involves to start out with a very low current density. And the reason is you want to be below the diffusion limiting current. This is to give us a nice solid deposition or plating out so that we get good adhesion. Then we raise the current above the diffusion limiting current, and now you start seeing evolution of hydrogen or deuterium. And as it continues to plate out, the palladium chloride or nickel chloride in the solution is plated out, and ultimately, now this is really an exponential curve that goes on out, but ultimately it gets down where the solution clears, and then we typically raise the current level to stabilize the material on the electrode. So this is the process that we've used, and we've been primarily focusing on nuclear products. You know, one of the questions was, you know, prove it's nuclear. If someone can prove it's nuclear, then we'll fund it. Well, remember when one neutron, if they can produce one neutron, that would be enough. You know, this was in 1989 when they were making their comments. Well, a year ago, we got a patent that on the production of high energy neutrons, it was actually awarded to the Spay War for producing neutrons. We haven't seen a lot of funding based on that patent. But recently, one of the blogs, I think in Italy, said that the U.S. government has officially recognized cold fusion because they have given a patent for this process. One of the other experiments that we've done is looking at deuterium uptake, and this was done published in 1994. After we do the initial plating, when we raise the current above the diffusion limiting current, within just a few seconds, then we reverse the current and look and determine how much hydrogen had been, or deuterium had been deposited at that time, which then came out. And since it takes twice as many electrons to plate palladium as it does with the deuterium, so 2/3 of the energy along this line is, let's say, this 8 seconds, would have been plating out palladium, 1/3 would have been plating out deuterium, and when we reverse the current, we see that we're getting, you know, now there's some, you know, where do you really put this second line, but we see that we're getting high loading in just a matter of seconds as we're plating out. Other experiments we did, published this in '99, showed that the excess enthalpy also occurs fairly quickly. You know, initially it's endothermic, and then very quickly shifts to exothermic, and you see the production going up. So again, more evidence. I threw the Galileo protocol up here because they decided, hey, if we had an experiment, this was another idea. If we have an experiment that a lot of people can do and they all get good results, then someone will have to recognize that this is valid, and we'll all get funded. So the idea was, let's do a protocol that if people follow, they will get results. And so Pam Voss very carefully wrote down a protocol for people to follow, and this was tested with a group of about a half a dozen different people tried it. Now, unfortunately, all of these half dozen people were scientists, and they all thought they had a better idea. So I don't know how many actually followed the protocol. The interesting thing is, though, most of them got results. And I remember the Littles in Texas put a thing on, a little video on the web. They said they had 7 cells running. They were all producing excess heat. They went straight to a high current level. They didn't start out with a low threshold. And when we had done that in some of our experiments, we saw, first of all, you don't get very good adhesion, and second, the plating is very mossy. But it's still, you know, they were very excited about it. 2 weeks later, they completely changed for some reason. I guess that's typical. But others saw also, using CR39, saw that they were able to produce particles, and these were people at SRI, Berkeley, several people, Oriani, and others all saw evidence of particles in the CR39. So the takeaway here is that co-deposition must be pretty robust, because it's hard to screw it up. Okay, now let me jump to the Let's Hagelstein paper. They tried co-deposition, and Dennis Letts has actually made a very nice calorimeter. They've done a lot of work in this calorimeter, and so they tried the SPOT protocol now. 0.3 molar lithium chloride, 0.5 molar O5 palladium chloride, and E2O, following a current profile similar to what Bowen had put together in the steps. And I have found out, yes, magnets were used for this experiment, and they did not see excess heat in this experiment. So, now, for reasons known only to Dennis and Peter, they changed the electrodes. They modified, here's the anode, copper substrate on the cathode. They reduced the lithium chloride by a factor of 2. They reduced the palladium chloride by a factor of 40. And rather than starting at a low plating current, they started at 500 milliamps per square centimeter. And when they did that, they saw excess energy and excess heat. So here's a picture of their cell. They had one electrode here that was their inert electrode, and they used this for calibration. They had a second electrode inside this platinum anode that was the copper foil that then they co-deposited the palladium onto. So the way they conduct the experiment was for the first 800 minutes they calibrated the CVAC calorimeter, and they did this with D2O lithium chloride just operating at 500 milliamps per square centimeter, what was the current level they're planning to operate. Then, at this point, they added, and this is really interesting, 0.44 milliliters of palladium chloride that they bought from Sigma Aldrich, 0.5% by weight, 10% HCl, and this was in a water-based solution, light water-based solution. So they actually added light water, not a lot, but light water to the cell. Now this challenges one of the early assumptions, and that was that hydrogen was a poison for these experiments. We don't know, but clearly it wasn't in this case, because when they did, what happened was immediately the excess energy went up. It operated, stayed for a while, and then they replaced the D2O with H2O, and it dropped, and then exponentially came back down. A lot of excess heat, very interesting experiment. Again, probably will lead to more questions than answers. So important events in the search for excess heat and palladium, we have Spock and Mosier Boss and others showed that co-deposition from palladium and deuterium works in a solution of lithium chloride. In ICCF 15, McCoubrey and his co-workers at SRI showed that some conditions must be met to replicate pond splash and excess heat. And this is where the heavy loading of 0.85 to 0.95, long waiting periods, 2 to 4 weeks, and then in ICCF 17, Peter gave a presentation, talked about something and mentioned the superabundant vacancies, and one of their experiments they found that one parameter only increased by 340% with an increase of 13 degrees in cell temperature, and that was the number of vacancies in the cathode. And the term superabundant vacancies is one that they use. And here's what it is. And this comes from Bukai was the initial author of this, and then other authors in 2010 published them, and this is where I got this drawing. But here's your normal face-centered cubic where you've got the metal lattice, the big face-centered cubic, and then the hydrogen or deuterium in the interstitial sites. And when the superabundant vacancy occurs is when you actually remove the metal hydrogen and or the metal, and so you get a vacancy here. And what can happen in that vacancy is it can actually trap up to 6 deuterium or hydrogen atoms. And as you see it here, here's 1, 2, 3, and there would be 4, 5, 6 on the other side here. And Bukai claims that this is actually a more stable loading than any of the other loadings. So the hydrogen is stable there. So and based on this, you get a maximum loading ratio of 4 to 3, so 1.33. Now, part of this loading is because we have now removed the metal, so the number of palladium or nickel atoms is reduced. But so you get a maximum loading of 4 to 3. Some of the things, and several of the papers that Bukai wrote, and again, he's I guess a metallurgist or a material scientist. One of the important recognitions is that it's the most stable structure in the metal hydrogen or metal deuterium alloys. In fact, a defect structure containing a large number of vacancies. In all metals investigated by ion implantation experiments, hydrogen ions are trapped in the vacancies up to 6 per vacancy with rather large binding energy. In the metal hydrogen alloys, a high temperature, high hydrogen pressure, lattice parameter, nickel and palladium decreased over several hours to a limiting value of minus 1.5% smaller. So, when originally we thought the lattice expanded as we added more hydrogen or more deuterium, Bukai says that when you have superabundant vacancies, it actually contracts. And there's a possibility of creating SAVs without extreme conditions, mainly electrolytic deposition. Now, the way he was creating was bombardment and all sorts of stressing of the lattice. And then in one of his papers, he says, oh, by the way, with electrolysis and electrolytic deposition, you can actually build them in, and the stable structure should be reached directly as the H and metal items are deposited simultaneously, incorporating the vacancies in the appropriate proportions. Connecting the dots on this one I found very interesting, and in light of some of the results that we just heard, the briefing we just heard about everything from ultrasonics to other ways, other forms of using the lattice. Shalani and his wire and the magic treatment he goes through to prepare it so that it will be successful. If you read what Pantelli has done and how he prepares his electrode, by cycling vacuum, and then hydrogen, and then a cycle and high temperature, you know. So I begin to wonder, are they in fact creating and ultimately loading superabundant vacancies? That's a suggestion. I don't know if that's the case. So observations, you know, co-deposition has been used successfully by a wide variety of experiments. We don't know, you know, what's the role of the magnetic or electric field, but clearly they are important. And different protocols, here's an interesting suggestion. Can different protocols lead to different reaction paths? Is there a heat protocol? Is there a particle protocol? And that has been suggested. Was the Flashman-Pons experiment really a co-deposition experiment? And Peter's the one that suggested this, I believe, and that is that did enough palladium come off of the rod, off the palladium wire, and then get redeposited so that it became a co-deposition experiment, and that's why it took a long time for the loading period. Don't know. That's subject to good discussion. What are the role of superabundant vacancies? And were Flashman and Pons lucky with their protocol? You know, I think in the paper, the phrase they used that the Flashman, in some respects, the Flashman and Pons experiment might be considered a bad experiment based on this. I'm probably not putting words in your mouth here, but and then co-deposition produces both high surface area and SABs, and so this raises a question: are SABs involved in the gas-loaded nanoparticles? So far, the main thing I've learned by studying this is that there are a lot more questions. I'm learning a lot more things that I don't know rather than what I do know. So once again, I'd like to acknowledge Mitchell Swartz and the team. I know didn't do it all alone. Stan Spock and Pam Mosier Boss and the Spay-War team who supported me for a long time since I was on overhead, and they were trying to earn or pay direct funding. Dennis Letts and Peter Hagelstein, who collaborated and answered a lot of questions and were patient with my questions. And then finally to all of you for contributing and continuing to work in this field. Thank you.
Frank, very nice. Two questions. One, in addition to loading, I think it's always been acknowledged you need a flow. And you haven't said anything about that. What do you know about it? Second thing is the